let's go over one last topic. So, chemical reactions, we already know from our previous studies that we have reactants go in and out come the products. And we also know that you need a certain amount of energy. We've seen potential energy diagrams already. So our reactants might start with some energy, and then we have to input energy, and that's called the activation energy that's needed in order to get the chemical reaction going. And then we get the products at the end. And if we have more energy at the end, then we know that energy exited or went in, and it's endothermic. If our products end up being all the way below our reactants, then we know that we've got less energy at the end than we did at the beginning, and energy exited, and we had an exothermic reaction versus an endothermic reaction. So we can do some things to make chemical reactions happen faster or slower. So first, I just have a basic definition of reaction rates, and that's how fast the reactants are going to chemically change into the products. And there's a little bit of a theory about what has to happen with the molecules. So this is called the collision theory. And what has to happen is these molecules have to do a couple of things. In order to get the reactants to form into the products, we're going to need the reactants to collide. And they're going to need to collide in the right position. And they're also going to need to collide with enough kinetic energy. So there's a few different factors that can affect how fast or how slow a chemical reaction occurs. Those factors include temperature, the concentration of the reactants, the surface area of the reactants, if there is a catalyst, or if there is an inhibitor. So pause for a second, and on the next slide, I'm going to have you try to rename these off of from the videos that we've watched the last couple of days. So take a minute, see if you can identify what the factors are that can affect the rates of reactions. These were all given in the videos that you watched throughout the past couple of days. So let's start with this first one, the temperature. If we increase the temperature of a reaction, you have to think about what's happening to the molecules. The molecules are going to move faster if they have more temperature to them. So that means they're going to have more energy. That's going to allow for those molecules to collide more often. It's going to allow for those molecules to collide with more kinetic energy. So in that case, our reaction is going to happen faster. In the videos you watched, we saw a reason for why it is that we take light up necklaces and things and put them into the freezer to extend their life. And that's because when we decrease the temperature, we are making those molecules move slower. And that means that there's going to be less collisions happening and less energy with those collisions. And so the chemical reaction is going to happen slower. And so that's going to preserve those chemicals that's in those glow-in-the-dark bracelets. And so then you can take them out and the reactions will start to occur more and it will light up more. One of the videos also showed how if you take those glow-in-the-dark necklaces and bracelets and you put them in warm water versus cold water, you could actually turn off the lights and see that the warm water were lit up brighter because of those faster reactions that were happening. And if you put those glow-in-the-dark bracelets in cold water, they are dimmer. And that's because those chemical reactions were happening slower. Next is the effect on concentration. So if we have more reactants, a higher concentration, so let's say that I have a 10 molar concentration of hydrochloric acid as one of my reactants. Well, that means we're going to have more of this particular molecule in the beaker, and so they're going to collide more often. And so that's going to make the reaction happen faster. Now, what if I use a really weak concentration of hydrochloric acid? Well, that means that the reaction is going to happen slower because the reactants are going to collide less often. So if we want to see lots of bubbling happening and a chemical reaction happen really fast, I'm going to give you a really strong acid. If I don't want it to happen very quickly, I can give you a really weak concentration of acid instead. Next is surface area. So surface area, if I have an increase in surface area or I have a high surface area, that means that I'm going to have lots of small pieces. So think about lots of little granules of sugar. So if I've got a high surface area, lots of little pieces of sugar, then we're going to have the ability for the collisions to happen more often and faster. So we're going to get a faster chemical reaction. Now, if I have a smaller surface area or I decrease the surface area, now that doesn't mean smaller pieces, that means I've got a large chunk. So in this case, think about a big cube of sugar. And so the molecules that are here in the middle, it's hard for the materials to react with those in the middle. And they can't get to them and they can't collide with those inner molecules. So the reaction is going to happen slower. If you think about putting a bunch of little granules of sugar into some liquid, these are going to dissolve faster. And the reason is that the water molecules can each interact with each of those little molecules. Whereas if you put a big chunk of sugar into the water, the molecules, it takes time to first interact with those on the outside before it can interact with those on the inside to get it dissolved. So it takes longer for that large cube to dissolve. So a decrease in surface area means you're going to have a big chunk and it's going to take longer for that reaction to occur because the molecules can't react with those that are in the center. Whereas if you have a high surface area, lots of little pieces, then they're going to be able to react with every little piece and the reaction is going to happen faster. Next, catalysts can affect how fast a chemical reaction occurs. What a catalyst does is, if you remember from our potential energy diagrams, we've got our reactants going in with a certain amount of energy, and we have to activate it. So here's our activation energy that's needed to get the reaction going, and then finally our products have energy. Well, here's what a catalyst does, is it lowers that activation energy so that way the reaction can happen faster. Some of the times that catalysts and catalysts are often called enzymes in your body and in the foods that we eat. So enzymes actually help keep your body at a certain temperature, and they make sure that certain biological reactions happen at a faster rate. Now, we have to remember that these catalysts are not a part of the chemical reaction, so they can be used over and over. Your body doesn't have to make more and more of them all of the time. Another good example of a catalyst that I like to talk about are catalysts that help you digest certain foods. For example, your body makes one catalyst called lactase. This is an enzyme that helps you digest milk. And a lot of times, most people, as they get older, their body stops being able to make very much lactase, or the lactase doesn't work properly, and so then you're lactose intolerant. This happens for over 50% of our population as they get into adulthood past the age of 18. They become lactose intolerant because this enzyme, this catalyst, is no longer being produced by your DNA to help you with digesting milk. Okay, so that's an interesting example of catalysts. Catalysts, also known as enzymes, are going to help speed up that chemical reaction. So here's what happens with that potential energy diagram. Here's the energy of our reactants, and normally we'd have to get a certain amount of energy here, but the catalyst, when we add that catalyst, now we don't have to get as much energy. So the goal of the catalyst or enzyme is to lower that amount of energy that we need to get to. And then finally, we've got inhibitors. Inhibitors do exactly what it sounds like they do. They are going to slow down the chemical reaction. And just like a catalyst, they're not a part of the reaction. And so what they do is they actually bind to any catalysts or enzymes around, and they prevent it from speeding up the chemical reaction. Inhibitors are used in the preservation of our food. What we do is we add these inhibitors into our food, and it stops any sort of reactions from happening that would cause decomposition to occur. And so that helps stop our foods from becoming stale or moldy. So let's look at this worksheet. In image A, I'm trying to show you differences in concentration. So in this first image, we can see that we have a low concentration of reactants, not very much. And in the second image, we have a higher concentration of reactants. And so the instructions say to identify which image will the faster rate of the reaction happen. So image 2 here that I'm circling in green is going to happen faster because of a higher concentration. Now in part B, I'm showing you differences in temperature. They both have the same concentration, but one is at 25 degrees and one is at 35 degrees. And chemical reactions are going to happen faster at warmer temperatures because the molecules are going to collide with greater energy because they're moving around faster. Letter C, I'm trying to show you differences in surface area. And so here we have one big solid chunk, or we've got lots of little pieces. And so the solid chunk is going to have a low surface area, and the lots of little pieces is going to have a high surface area. And so the reaction that's going to happen faster is going to be the one with the high surface area to it. And then finally, I have some potential energy diagrams for you. And if it requires less activation energy, so this here that I'm highlighting in green and blue, that's your activation energy. And so if it requires less activation energy, then that chemical reaction is going to happen faster. So this one here that I'm circling in red is going to happen faster because if you don't need as much energy, then the reaction, those molecules can collide more easily with enough energy to make the chemical reaction occur. So within the last couple of minutes while I went through each of these, I explained the different choices as well. So if you missed that, go ahead and go back over the reason that I circled each of these different ones that would happen at a faster reaction rate. This last part is a review of those potential energy diagrams. So if we're looking for the activation energy of the uncatalyzed reaction, we're looking at how much energy does it take to get from the reactants, which I'm highlighting in red here, all the way up to our activated complex, which would be right here. So it looks like my reactants start at an energy of about 70, and my activation energy, or my activated complex, is at about 130. So that means that the amount of energy I need to add is going to be about 60 joules of energy in order to get activated and uncatalyzed. Now, what if I have a catalyst added? So that means, again, I'm starting at the reactants of about 70, but now my activation and activated complex is lower. I only have to get up to about 100. So that means that I only have to go from about 70 joules to 100 joules in order to get this reaction to occur. So if I have a catalyst, I only need an activation energy of about 30 joules for this. The next question says, what is the potential energy of the activated complex? Well, it depends on if I'm catalyzed or uncatalyzed. If I'm an uncatalyzed reaction, then my potential energy is 130. If I'm catalyzed, then my potential energy is 100. Now, if you remember how to calculate delta H, the delta H is the energy of the products minus the energy of our reactants. So if we look at this graph, our products look like they're at about 30 joules of energy, and our reactants look like we start at about 70 joules of energy. So our products minus our reactants would be 30 minus 70, which means that our delta H for this reaction would be negative 40. Now, this doesn't change if we add a catalyst. Notice that my reactants are still at 70 no matter what, and my products are still at 70. The only part of the graph that changes is this part that I'm highlighting in yellow right here, is that energy that's needed to be activated. And so that means that our delta H is still going to be negative 40 joules of energy, regardless of if I have a catalyst or not. Now, if we go in reverse, all that means is that now over here, I'm highlighting and I'm circling it in green. Over here, now those are the reactants, and over here now, these are the products. So remember that delta H is calculated by taking our products minus our reactants. So now our products are 80 and our reactants, are 70 and our reactants are the 30. And so now our delta H is going to simply be a positive 40. So all it does when we run in reverse is it changes our reaction from whether it's exothermic or endothermic. So energy went out of the system when we go forward. So by looking at this graph here, I would say that this is an exothermic reaction when we go forward, but when we go backward, it's endothermic and we get a positive delta H. And then finally, letter G, why is the catalyzed reaction faster? Well, because we don't have to add as much energy into the reaction, which I'm circling in red up there. We don't have to add as much energy. So we've got some real life questions. Why does milk sour less rapidly in a refrigerator than it does at room temperature? Well, remember that this is going to slow down the molecules from interacting. And so if we slow down those molecules, we're going to slow the chemical reactions down that cause spoiling. And so we're going to have less of that chemical reaction occurring, and so they're not going to spoil as quickly if we keep it in the refrigerator. If you put your milk out on the countertop, now those molecules are going to speed up and they're going to be able to go through the chemical reaction faster. Number 5 says a manufacturer of flash bulbs containing magnesium powder wants you to achieve a longer duration for the flash period. So remember that if you've got a powder, you have lots of little pieces. So you have a very high surface area. And so your chemical reaction is going to happen fast. But if I gave a big chunk of magnesium with a lower surface area, then I could get the chemical reaction to happen fast or slower, because first it has to happen with the molecules that are on the outside, and then once the chemical reaction occurs with those on the outside, then it can get to those molecules that are on the inside. So I can lower the surface area by having one large chunk of magnesium instead. So number 6, why does the reaction rate increase as the concentration of reactants increases? Well, if there's more molecules moving around, then there's a greater chance that they're going to collide with each other. And when they do collide, they're going to collide more often as well. And they're going to be moving around, and they've got that greater chance of reacting then. And then finally, the last question says, how does a catalyst speed up the chemical reaction? They lower the activation energy. All right, we're going to be having a quiz over this. So if you need to, rewatch the video and make sure that you rewatch any of the videos I posted on Schoology to help you go over it as well.